Let me click record. Okay, guys, we're back again. Okay, and Levi was a little bit on the detail side on that one, so well, I should shout into the microphone, wake you up again. So it's hard to make this stuff entertaining, especially in a lecture when you really have to go through a lot of detail and background and theory and so on and so forth. It's a lot easier for me to do some examples. And I think a lot of times it's easier to learn this stuff from examples as well. So we're going to do that right now. So we're recording again. We're back online. Looks like almost everybody is back. So I'm going to go ahead and get started. So there is a document on Blackboard in session 6 called Confidence Interval Practice Problems. There's actually 3 of these documents. I'm going to start with this one, Confidence Interval Problems. I'm going to take a look at this, and we're going to work this out a little bit. So let's take a look at this. The first problem that's here is not really a confidence interval problem. It says the mean of a population is known to be 160, and the standard deviation of a population is known to be 20. It asks you properties about that observation. What would be the probability of a single observation being selected at random from the population less than 154? We know that's a z-score. 154 minus 160 divided by 20. It's a negative. It's below the mean, so it's negative. And then we look up the z-score in the area. So these are all things that have to do with single looks at a population. It's kind of a warm-up. So I'm not going to go over that because we've really kind of beaten that to death at this stage. Okay, but I'm going to go on to this next one, which is interesting. A random sample of size. What happened there? Where'd it go? Did I knock it off? Did I backspace over it? Of size, I am going to, I think I say it down here. Okay. A random sample of size 100, I got to call it. Okay, in fact, it's down here. Has a mean of x bar equals 100. Anytime you see me use x bar, I'm talking about a sample mean, not a population mean. Assume that the population is normally distributed with a standard deviation of sigma is equal to 30. Now notice, I'm giving you the population mean here. We almost never know the population mean. Okay, we almost never know mu, the population mean. We almost never know the population standard deviation. But in this case, just for this exercise, I'm going to make believe that we know what the population standard deviation is. Where might that occur? That might occur maybe in a census where we actually sampled everybody in the population. It might occur because we had a previous study that was very, very large, and we know from people in that previous study that that's what we would expect as the standard deviation of the population, of that same population. Really doesn't matter. In this case, I'm just giving it to you. Calculate the standard error for samples of size 100. Well, the standard error is the standard deviation for repeated samples of size 100, right? So what's that standard error going to be equal to? That standard error is going to be equal to sigma, since we know it, over the square root of the sample size, right? So what's that going to be? That's going to be equal to, what was sigma? 30 divided by the square root of 100, which is 10, which is equal to 3. So the standard deviation of repeated samples of size 100 from this sample, where x bar is equal to 150, repeated samples of that size is going to be a standard error or a standard deviation of the sample means of 3, where it had been standard deviation of population had been 30. Population much more spread out than the means of sample size 100. They're much closer together. Now, the interesting thing here is that we're just talking about this a second ago. I'm going to repeat it. You guys weren't available for this at the time. You were back on the lecture there. We never know the point value for a population. In other words, we virtually never know what the average BMI is for all Hunter students. Okay, that's a point value. That's a mean value for the entire population. We almost never know that. We also almost never know standard deviation, but we're going to cheat a little bit and say that we do. But in fact, we very rarely do. The other thing is a proportion. if I were to go out and sample 100 people and ask them, um, uh, 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 what color what would you like, red or blue, better? Right? And we found that 30 out of 100 people liked blue better than red, or red better than blue. We'd say that the proportion that liked red was 30%. Right? The proportion of the population we're guessing is 30%. We really don't know the entire population. We only know that sample of 100 was 30%. So the actual point value, the mean or the proportion that represents the entire population, is out of our reach. It exists, it's a real number, but it's not anything we'll ever know for sure. So the best we can know is what our sample mean is, or our sample proportion is. And the reason why that's important to us is that we're going to use that as a starting point when we take a sample. But then, since all we know is that the sample mean or proportion is some number, we want to know how well we understand that relative to what the real population mean is. And based on what we learned so far, even though we can't predict how close to the mean that is specifically, we can construct an interval that we can predict is within a range that will capture the actual population mean. And we call that the confidence interval. So if I want to compute a 95% confidence interval, the mean of this population for mu, I'm going to say that it's going to be the mean, the 95% confidence interval is going to be equal to x bar, the mean that I calculate, plus or minus, right? What's it going to be plus or minus? It's going to be plus or minus a z-score that represents the level of certainty that I want, times, right, my standard error, how variable my sample is. And that's based on, what is that standard error really? It's sigma over the square root of the sample size. That's sigma, right? Okay, so let's see, where am I going to go with this now? Okay, well, for starters, x bar in this case is 150. Right, it's going to be 150 plus or minus, right? Plus or minus, above or below. Remember, we could be looking on either side. We could have underestimated the true mean or overestimated. It could be on either side the true mean. Plus or minus the z-score. Now the z-score is going to depend on how certain we want to be, what our confidence interval is. So for 95%, we're going to use 1.96 for the reasons that we spoke about before, times my standard error. Okay, now of course my standard error is really equal to, it's 150 plus or minus my standard error. Since I know my sigma, since I know what my population standard deviation is, I can use that 1.96 plus or minus 1.96, a z-score, times my standard error is 30 divided by the square root of 100, my sample size. So what is that going to be equal to? It's going to be equal to 150 plus or minus, okay, I'm taking a long route here, 1.96 times my 1.96 times 30 over 10, which is 3, is going to be equal to 150 plus or minus, well, 1.96 times 3 is going to be a little under 6, so it's going to be 5.8, see, 5.88, I think. Am I right about that? Minus, plus or minus 5.88. What do you think would be a good thing for us to call this plus or minus? Got a good name for that? If I told you, oh, that guy looks like he's 50, give or take 10 years. Yeah, it's the margin. How about margin of error? Let's call that our margin of error, right? I'm going to call this part right here our margin of error. Okay, so let's add and subtract that from 150. And what do I wind up with? I wind up with a confidence interval, which is, let's say if I subtract it, it's going to be 144.12. And if I add it, it's going to be terrific. There we go. That's my 95% confidence interval. I'm 95% sure the true mean is between those two numbers. Now, what about a 99% confidence interval? The only thing that's going to change when I start talking about a 99% confidence interval is that instead of using 1.96, 2.58 exactly. It's going to be 2.58. Okay, and 2.58 times 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 square times 3 is going to be times 3. It's going to be 150. Let's see, times 3 is going to be 7 point. Thank you, 7.4. Okay, that's our margin of error. Since I'm adding and subtracting that to 150, my 99% confidence interval is, as I would expect, wider than my 95%. What is it? And add it to it should be simple, right?
157.7.
Here we go.
Wait, why'd you times it by 3?
I'm sorry?
Why'd you times it by 3?
But 3 is the standard error. 2.58 times 3. Remember, it was 30 divided by the square root of 100. Sigma
Oh, okay.
sigma over the square root of n, right? N is
Okay,
100.
I thought it was the square root of 36. But okay. Oh, okay, sorry.
The right sample size was 100. Okay. So, and now if I wanted to do this is 99% confidence interval. If I want to do the 90% confidence interval, I would just substitute 1.64 here, and it would become much narrower.
How do we know
This is all what we've been doing already, right?
Yep.
Yeah.
Yep.
how do we know what to replace the 99 comes from the empirical formula, right? The 95, the 90.
Well, not from the empirical, from the Z table.
From the Z.
Right,
So we would
1.96
look up
represents
99.
95% of the middle
We would look up
values. Yeah,
95.0095.
exactly,
And
exactly.
then the 99 we would look up 0.0099.
The 0.0, no, we would look up 0.5% on one side and 0.5% on the other side, which would be a z-score of 2.58 on either side. The question is, where did we get these numbers from? I'll show you again where we got the numbers from in a second. Okay, take my word for it for the moment.
The numbers we're always going to have?
Yes, for a 95% confidence interval, we will always use a z-score, right, of 1.96. For a 99% confidence interval, we will always use a z-score of 2.58. And for a 90% confidence interval, we always use a z-score, missed the right key there, z-score of 1.64. And we talked about that earlier, but I'll illustrate again where those numbers came from. Okay, so let's just stick with those for the time being. Okay, so now, what about this one? A random sample of size 36, that's the next problem. I think maybe you go ahead and sound the next problem. As a mean of 150, assume the population is normally distributed a standard deviation of 30. Calculate the standard error. Okay, well, what's the standard error going to be equal to? The standard error is going to be equal to, whoops, let me keep it up there. Standard error is going to be equal to sigma over the square root of n, which is equal to 30 divided by the square root of 36, which is 6, is going to be equal to 5. Exactly. That's exactly right. That's our standard error. Now, compute a 95% confidence interval. Well, a 95% confidence interval is going to be 150, right? We're doing the same thing, except the only difference here is the standard error. The sample size, the standard deviation, population is the same. It's just the sample size has changed. Plus or minus, okay, 1.96 times the standard error. Okay, and what's the standard error? We just calculated it before. It's equal to 5 times 5, okay, which is equal to, let me put this at 150 plus or minus. Okay, so I'm going to round this off to 10, since I don't have to sit here and think. Okay, so plus or minus 10 would be 140, comma, between 140 and 160. Okay, we know it's slightly different than that if I really calculated it, right? So that's my 95% confidence interval. Notice how much wider it is than the numbers we got up here. Why is it wider? Because the sample size is smaller, which means the standard error stays a bigger number because we divided by the square root of n. That n was a smaller number. So standard error became a bigger number. If we wanted to do it again for 99%, we would just use 2.58. 90%, we just use 1.64, and so on. You guys online, are you okay with this so far? Let me open the chat box here so I can see. Okay, good. Not real hard, right? So far, it's reasonable. Okay, so now I'm going to throw a real curve in here. A random sample of size 15 has a mean of 150. The standard deviation of the sample is 30. What did I just change here? What was the biggest change besides the sample size? What big change do you see here? What did I not tell you?
The population.
Sigma. We don't know what sigma is. We don't know what population standard deviation is, right? What am I going to have to use? I'm going to have to use the standard deviation of the sample instead. That introduces a new element of uncertainty, especially since it's a small sample size. Okay, so now I'm going to calculate my standard error first. It says calculate my margin of error. I'm going to calculate standard error first. Okay, so the standard error, right, is going to be equal to sigma. I don't know sigma. I have to use the standard deviation instead over the square root of n. Okay, well, what is that? That's going to be equal to.
Wait, where did you put that on the page?
Can you see that? I don't. Let me look behind. Oh my goodness, what happened here? You guys have been staring at that box over there for the whole time?
No,
Yeah.
I was looking at the.
Oh, you were looking at the computer. Okay, good. All right.
All right, so it's the standard.
Okay, hang on a second. I'm going to make this a little bit bigger too. Standard error is equal to standard error is equal to the standard, because I don't know what sigma is. I got to use standard deviation of the sample now. Standard deviation of the square root of the sample size. So what is the standard deviation? It's 30, just like it was before, divided by the square root of 15. Right now, I actually have to do a calculation now to calculate that. Let's see, calculator. Clear. Let me clear out memory too. Okay, so 15, the square root of 15 is that, memory plus, clear, and so 30 divided by the square root of 15 is about 7.75. Okay, that's my standard error. Okay, now I have to calculate my margin of error. And what was my margin of error again? Okay, now that's what I used. Remember before it was 150 plus or minus my z-score, right, for 95% confidence interval, we called it 1.96, times my standard error. Okay, I've calculated my standard error, right? This is my margin of error in here, that I'm going to add and subtract. Now the problem is, I know what standard error is. It's 7.75. 7.75. I can calculate that. But now I don't know what my population is. Population standard deviation is. Sigma. I don't know what it is. So, and it's a small sample size. I can no longer justify using the Z distribution, the Z table. I have to use a different table, which will give me a different value for Z. But instead of calling it Z, we're going to call it the T distribution. Okay, and I'm going to go over here, and I posted it on Blackboard. Here is a T table, right? So for a 95% confidence interval, the value of T that we would use if we had an infinite sample size, in other words, a whole population, would be 1.96. That would mean if we had to use the whole population, we would know what sigma is, right? So the only time we would use 1.96 is when we knew the population standard deviation. But if we have a smaller sample size, this is degrees of freedom, which represents sample size. If we have a smaller sample size, we would have to use a different number for the t value instead of the z value. So for instance, what was our sample size here?
15.
15. However, a little bit of a tricky thing here. We're going to use degrees of freedom, and degrees of freedom is typically n minus 1, sample size minus 1. So the degrees of freedom is going to be 14. One of the ways you can look at that is you can say to yourself, when you have only one number, you have no degrees of freedom. When you have two numbers, you can choose one or two numbers, you have 1 degree of freedom, this or that, right? So we're 15 degrees of freedom, 15 sample size of 15 is a degrees of freedom of 14. So if I go over here to the 95% confidence interval, the t-score I should be using instead of 1.96, I need to use 2.131.
Oh, you don't use 14?
Oh, I'm sorry, 2.145. I got, what do you call it? I kind of lost my horizontal. Yeah,
Why
it
do
was
you use that column?
because it's a 95% confidence interval.
Oh,
See
okay,
that.
that's easy.
Right,
now.
see it up there?
Okay, yeah.
Now remember Levi in the lecture mentioned that, oh, you got to go, if you go to the table and you take 95% and subtract it from 100 and you get 5%, divide that in half to get 2.5%. The reason why he was saying that is because some of these tables, let me see if I can't make this bigger.
Well, we could use this table.
Yeah, you can use this table. You'll have this table from now on. Some of these tables will only show you the right tail probability, which is 0.025, 2.5%. But it's really the right tail is 2.5%, the left tail is 2.5%. So that means outside of the middle section is 5%, which means you're predicting the middle 95%, which is your 95% confidence interval. Kind of convoluted, right? But instead, you could just go up here and use this. So this is the column that we're using, and we're using it based on the sample size. Why does the sample size matter? Why does the t number change with sample size? Because the larger the sample size, the more confidence we have in the estimating using standard deviation to estimate the population standard deviation. And in fact, once we get up to a large sample size like 100, well, look what the t-score is, 1.98 instead of 1.96. A lot of times you'll just say, let me use the z-table. I'm not going to bother using that because I have such a large sample size. Levi is a statistician, so what did he call a large sample size? 300 he called a large sample size, right? Okay, most normal people would call 100 a really nice sample size, right? Some textbooks just say, oh, just use 30 as a large sample size, use a z-table.
For our class, it's 30?
For our class, I will give you, since Levi does it one way, I do it another way, Professor Weicker does it another way, somebody else does it another way, I'll give you some sort of hint on what I should. I'll give you some sort of hint on whether to use the z-score or the t-score. Right? Okay. So now I'm going to show you. We can do this with SPSS also, right? SPS. What do you think SPSS does when it has a sample size of 100? Wait. Let me stop for a second.
Oh,
When SPSS calculates the confidence interval, which it can, right? You might have noticed one of the things that when you're on the test and then one of the homeworks, one of the things it calculated for BMI when we did that problem was the confidence interval for BMI. Now you know what that means, right? So one of the things you might know is go ahead and calculate it. If it was a sample size of 20, what do you think it used the t-test or the z-score or the t-score?
t-score.
Use it right. How about a sample size of 50?
T-score.
Okay, how about a sample size of 100?
T-score.
How about a sample size of 300?
Z-score.
Use the t-score. How about a sample size of 5,000? How about a sample size of 5,000? It uses the t-score. Why does it do that? Because
So SPSS
it always uses the t-score. Why does it always use the t-score? Because the t-score might be 1.9611600001, just a little bit different for a very large sample. But it's a computer; it can afford to do that. We make the compromise of making kind of a decision for z-score, t-score out of convenience. See, if this is your table and you used and the sample size were 200, you'd almost be forced to use the z-score. Why? Because it doesn't tell you what the t-score is for 200, right? So that's why, for our purposes, most of the time, over 100 use the z-score, right? Because that table doesn't have it. I could tell you go to another book or go online, find out what the t-score is for a sample size of 200. But why bother? It's so close. So for my purposes, I like to say 100. Why? Because the table I use the most just happens to have the largest value for t it has is 100, right? So then if it's bigger than that, I just use the z-score, right? It's just practical. It's just a practical thing. But in reality, you should always use the t-score unless you know the population standard deviation, and that's exactly what SPSS does. Okay, so if we wanted to calculate this, we would use for a sample size, what was the way I said, 2.131 or something like that? 2.1.
145, the t-score?
Yeah, what was the t-score?
2.145.
Was that one? Are you sure about that? Yeah, you're right. Look at that, 2.1. Oh, yeah, I went across the wrong way. You're right. I picked the wrong number. What I did myself. So instead of, okay, yes,
What does it ask? What does it say 95% for us to go to 95%?
over here.
Oh,
It's
you're
actually, yeah,
calculating
I'm doing the next part, yeah.
Oh,
Okay, that's just asked for the margin of
Oh,
error,
okay.
right? So actually, I could do that now. I could say, what's the margin of error? It's like plus or minus 2.141, 2.145. Oh, that's still in there. I don't, okay, times, I'm a 2.145 equals 16.6. 6. So it's 150 plus or minus 16.6. And that's going to come out to be, I'm going to call it 16. That's going to come out to be 134 to 176. I'm just getting this done quickly. So you realize, of course, you would actually add and subtract that. Okay, that's my 95% confidence interval because I used the t-score. Okay, so now what about a 99% confidence interval if you had to use a t-score? Well, you just use the other column, right? Where's 99%? Here's 99%. And if we're a sample size of 15, it would be 2 point, yeah, 2 point, I lost it. 14, 2.99, 2.977. Okay. And if the sample size got bigger, you would see that the t-score, the t-value would get smaller. Okay, well, how about, let's do one more. And this last one is, let's see, how about a proportion? A major metropolitan newspaper surveyed a random sample of 200 voters. They asked whether they planned on voting for a new bond act. 110 of those surveyed said they planned to vote yes. Okay, now I am going to call P the true proportion, true point value for the entire population. I'm going to call P cap. When I could draw this, but you know what I mean. P cap. It's got like a P with a little cap on it, little funny little cap, right? P cap is my sample proportion. Okay, so now what's the 95% confidence interval for the proportion of voters in this population who will vote yes? Okay, well, what is that proportion? It's 110 said they were going to vote yes out of 200. So what proportion, what's P cap? It's equal to 0.55, right? 55% of the population says they're going to vote yes. Okay, so that's nice that that many are going to vote yes. But now, how confident are we of that? We can actually do a confidence interval for a proportion as well. And how are we going to calculate that confidence interval? Well, we need to know what the standard error is, right? Well, before we know standard error, we need to know a standard deviation as well. I'm sorry. We're going to calculate standard error. And how do we calculate standard error? Well, look at this. We have a formula for calculating the standard error. Standard error for proportions is equal to square root of the proportion times 1 minus the proportion over n, and then you take square root of the whole thing. So I'm going to do that over here. Okay, so it's going to be equal to the square root of, okay, and I like doing it this way because it's the same formula for Excel. Square root of 0.55 times 0.45, 1 minus that, divided by the sample size. Sample size was 200 voters, right?
Yeah.
Okay, so I'm going to go ahead and actually calculate that now. So clear. So it's going to be 0.55 times 0.45 equals that divided by 200 equals that, and then I'm going to take the square root of that. So my standard error is 3.5%, 0.035. Three and a half percent. Okay. So now, just like I did before, I can use that to calculate a confidence interval. P cap, let's see, 95% confidence interval. 95% confidence interval for P, right? Because we want to know what P is, right? Is equal to P cap plus or minus, plus or minus. Well, what number am I going to use here? Am I going to use a t-score or a z-score?
I would say it depends.
I'm going to use a z-score, and I'm almost always going to use a z-score. Reason why I'm almost always going to use a z-score is we're going to establish a rule that when we do proportions, that we're going to have a minimum sample size. The minimum sample size is going to be at least 30 people, and 15 have to be in each group. You can't have one group with 10 and the other group with 20. It's got to be at least 15 in each group, and so on and so forth. So I'm going to pick a minimum sample size. This is a pretty big sample. Got 110 in one group, 200 in the other group. So I am, for this purposes and for most calculations involving proportions, except when we do an SPSS, which is always going to use the t-score. For most of them, I'm going to use the z-score, which is 1.96. Okay. Occasionally, I'll warn you about it. Occasionally, I'll tell you might have to consider using the t-score based on the sample size. Okay, but I'm going to, for this, because it's such a large sample, I'm going to use the t-score here, the z-score here, 1.96 plus or minus. Where's my plus? Plus or minus. Okay, my standard error, which is 0.035, 3.5%. So this is roughly 1.96 times 2 times 3.5%, which is my P cap. P cap, what was P cap again? It was 0.55, right? 0.55 was P cap, plus or minus. Okay, for my sample proportion, right? 0.55 plus or minus, right? 1.96 times 0.035. I'm going to cheat and just call it 7%, like 2 times 0.035, plus or minus 0.7, right? 0.07.
It's 1 minus.
Plus or minus 1.96
times. Right?
Times. Yeah, I'm sorry. Yeah, times. Right, it's getting late. I'm getting more scattered as the night goes on. 1.96, 2 times that roughly. So it's going to be 0.55 plus or minus our margin of error, which is 7%. That's the same, that the margin of error. Look at that. Oh, 55% plus or minus 7% sounds like a poll, an election poll, doesn't it? In fact, that's kind of the way to do election polls also. So what's my confidence in my 95% confidence interval for the true proportion of people that are going to vote yes? Well, my 95% confidence interval is going to be 7 less than that, which is 0.48, right, comma, and 7 more than that, which is 0.62. Right? So it's between 48% and 62%. I'm 95% sure that between 48% and 62% of people are going to vote yes for this proposition or this bond bill. Am I 95% sure it's going to pass?
No.
No, because it overlaps 50%, right? Right? If I had told you the 95% confidence interval is 52 to 62%, you would have said, boy, I'm 95% sure this thing's going to pass. Right? I'm 95% sure Hillary's going to get elected. And look what happens, right? But now, at least here, we can see that now that we have this range of uncertainty, it helps us use this usefully. If all we knew was 55%, we would say, gee, it looks like it's going to pass, but I don't really know how certain I am. Here, I can say well, it looks like it's going to pass, but I'm not 95% certain it's going to pass, right? That's why we're interested in the confidence interval. If this had been 0.09 or point 0.1, right? Right. This had been 5%, and this had been 0.1, and this had been 0.55 and 0.65 or whatever, right? I got that right. 0.1 lower would no, it would have been 0.5. No, I'm still wrong. If this had been smaller, should have been smaller. If this had been 0.2, if a margin of error had been 0.2, this would have been 0.53 and 0.57, right? Well, then I'm 95% certain that it's not 50%, that it's above 50%. So I would have been 95% certain that the bond issue would have passed. Not 100% certain, but 95%. Yeah, thank you, Vicky. Exactly right. Yeah, I'm getting scattered. As the night goes on, this happens to me, right? So we can see, we can apply this to different kinds of situations, numerical variables or to categorical variables. In other words, proportions. I want to do one more thing, and that is I want to use SPSS to calculate a confidence interval. And I'm going to go in here, and I think I got SPSS started up already. And matter of fact, maybe I'll use BMI right here because we've already done that. Analyze, descriptive statistics, explore, and I'm going to ask it, I'm going to take that out of there. I'm going to ask it to do, here's our statistics, 95% confidence interval for the mean. Now you understand why, in addition to you telling it descriptive statistics, it wants to know, well, what do you want me to do? 95% confidence interval or 99% confidence interval? I'm going to leave 95%. Okay, that's under statistics. Okay, I'm going to click OK, and you'll notice that when this comes up, that among the other statistics that are shown here are mean and our 95% confidence interval. Not only that, it also calculates our standard deviation, and it might also do our, it's not on this particular analysis, but some of these will actually show you the standard error that it used to calculate it also. Oh, here it is. Here's the standard error right here. Right? Here's standard error. But it's basically 2 times that. You're going to add and subtract that from you're going to add and subtract that from the calculated mean that you have, the point value. Okay, so you can use SPSS to do this in most cases where we give you the data for it and so on and so forth. But we also have problems that involve, you having to do a little bit of math, but it's really pretty simple math once you get a little bit of confidence. Anyway, I really avoid using that word confidence because I said it 5,000 times tonight. Right? Once you get comfortable doing this, I don't think you're going to have too much trouble to it. It's relatively simple. Okay, guys, so let's call it a night, and we'll get back together. Now, remember, I'm going to be posting later on Blackboard, unless like I get a million objections or somebody's got a real reason why they have to be here on July 3rd, and I presume that's not the case because I think most of us probably would rather do this online since Blackboard's, they're going to screw up Blackboard anyway. I know it. And it's going to be a long weekend. It's going to be better if we don't have a long weekend. So I'll do it online and make sure we record it. And if necessary, if Blackboard doesn't come back online by that evening, I will email whatever materials or links to whatever materials that we're going to be using during that class. So have a good night. Good night.